Welcome back. In this video, we're going to look at examples of finding slope and special types of tangent lines for polar curves. Let's get to it. All right, so here's our first example. For r equals theta, we want to find dy dx and the slope of the tangent line at theta equals pi divided by 4. All right, so what we're doing in this problem is for this polar equation of r equals theta, we want to find the derivative dy dx and then evaluate that derivative at this value of theta to find the slope of the tangent line for that polar equation at that value of theta. And in order to find the derivative dy dx for a polar equation, we need to know the formula for finding the derivative or the slope of a polar equation. And that formula looks like this. Dy dx, the derivative or the slope, is equal to f prime of theta times sine theta plus f of theta times cosine theta divided by f prime of theta times cosine theta minus f of theta times sine theta. Now f of theta is just our function in terms of theta that r is equal to in our polar equation. In this case, that's just theta. So we'll have f of theta is equal to theta, all right? And then f prime of theta in this formula is just the derivative of f of theta. So in this case, f prime of theta will be equal to the derivative of theta with respect to theta, and the derivative of theta to the first power is just going to be equal to its coefficient, which is 1. We have 1 theta, so the derivative is 1. All right, so now we have f of theta and f prime of theta. Now we just have to plug these values into this formula to find dy dx for this polar equation. And once we have that derivative, we can evaluate it at theta equals pi divided by 4 to find the slope of the tangent line at that angle. All right, so let's set up our derivative. Dy dx is equal to f prime of theta times sine theta. F prime of theta is 1, so we're going to have 1 times sine theta plus f of theta times cosine theta. F of theta is theta, so we'll have theta times cosine theta, and that will be divided by f prime of theta times cosine theta. So we'll have 1 times cosine theta. So I'll write that down, 1 times cosine theta, and then we will subtract, right? We're subtracting f of theta times sine theta. And f of theta is theta, so we'll have theta times sine theta. Okay, so that's our derivative, but now let's simplify it a little bit. This will be equal to sine theta plus theta times cosine theta divided by cosine theta minus theta times sine theta. All right, and there's really nothing else for us to do at this point. We really can't simplify this derivative any further. The only thing left to do now is to plug in our value of theta to find the slope at that angle. And so let's do that next. We already finished the first part of the problem, which was to find dy dx, our derivative. Now let's use that derivative, dy dx, and evaluate it at theta equals pi divided by 4. All right, that's going to be equal to sine of pi divided by 4 plus pi divided by 4 times cosine of pi divided by 4, and that will be divided by cosine of pi divided by 4 minus pi divided by 4 times sine of pi divided by 4. All right, so we just replaced each of these thetas with pi divided by 4. Now we just have to evaluate sine and cosine at those angles and then simplify our slope. Now sine of pi divided by 4 and cosine of pi divided by 4 are equal to the same value. They're both the square root of 2 divided by 2. So if I continue our work up here, this will be equal to the square root of 2 divided by 2 plus pi divided by 4 times the square root of 2 divided by 2, and that will be divided by the square root of 2 divided by 2 minus pi divided by 4 times the square root of 2 divided by 2. All right, and now at this point, notice that we have the square root of 2 divided by 2 in every single term of this quantity, right? We have the square root of 2 divided by 2 in this first term, then it's in this term, it's in this term, and this term. So what we can do is reduce each of these terms by a factor of the square root of 2 divided by 2. Or another way that you could look at it is we could pull the square root of 2 divided by 2 out of both terms in the numerator and denominator, and it will look like this. We'll have the square root of 2 divided by 2 times 1 plus pi divided by 4, and then the square root of 2 divided by 2 times 1 minus pi divided by 4, and then the square root of 2 divided by 2 will cancel out with itself. All right, so however you want to do that is fine, but in both methods, you will end up with 1 plus pi divided by 4 divided by 1 minus pi divided by 4. All right, so just to review what we did there, we pulled the square root of 2 divided by 2 out of each of these terms. And so if you pull it out of the first term, you're left with 1. And then pulling it out of the second term leaves us with pi divided by 4. And then doing the same thing in the denominator leaves us with 1 minus pi divided by 4, which is what we have right here. And then those two factors canceled out. That's the same thing as reducing each of these terms by a factor of the square root of 2 divided by 2. Okay, so this right here is our slope, but we can make it look a little bit nicer. Instead of having this fraction in the numerator and denominator, if we multiply this by a form of 1, of 4 divided by 4, that will cancel out with this 4 in the denominator here, and we'll have a much nicer answer of 4 plus pi divided by 4 minus pi. All right, 4 times 1 is 4, 4 times pi divided by 4 is pi, and 4 times 1 is 4, and 4 times negative pi divided by 4 is negative pi. All right, and so what we found right here, 4 plus pi divided by 4 minus pi, is the slope of the tangent line at theta equals pi divided by 4 for this polar equation of r equals theta. All right, so all we had to do to find that slope was first find that derivative dy dx, which is what we found right here, and then we evaluated this derivative, which represents the slope, at the given value of theta, which was theta equals pi divided by 4. And plugging that angle into our derivative gave us this slope. Okay, let's take a look at another example. All right, next up we have this example. For r equals 3 plus 2 sine theta, we want to find dy dx and the slope of the tangent line at theta equals pi divided by 6. All right, so we're going to use the same process as we did with our last example. We want to first find that derivative dy dx, and then evaluate that derivative at this given angle to find the slope of the tangent line at that angle. All right, so let's work on finding that derivative dy dx. That's the first thing that we want to do. And we're going to use that same formula that we used in the previous example. Dy dx, or the derivative in polar form, is equal to this expression. All right, so let's find f of theta and f prime of theta, and then we'll set up our derivative. Now, f of theta is just whatever r is equal to in your polar equation, which means that for this example, f of theta is equal to 3 plus 2 times sine theta. All right, and now we also need to find f prime of theta, which will be the derivative of this expression. So we'll have f prime of theta is equal to the derivative of 3, which is 0, because the derivative of all constants is 0. But then we'll add that to the derivative of 2 sine theta, and the derivative of sine is cosine, so the derivative will be 2 times cosine theta. All right, that constant multiple carries over to the derivative. So now that we have f of theta and f prime of theta, we can begin to set up our derivative. So let's do that. We'll have dy dx is equal to f prime of theta, which is 2 times cosine theta times sine theta. So we'll have 2 times cosine theta times sine theta, and then we'll add that to f of theta times cosine theta. And f of theta is 3 plus 2 times sine theta. So we'll have 3 plus 2 times sine theta times cosine theta. All right, and then this is all divided by f prime of theta times cosine theta, and f prime of theta is 2 cosine theta, so we'll have 2 cosine theta times cosine theta, and then we will subtract, right, we have a subtraction sign here, f of theta times sine theta. And once again, f of theta is 3 plus 2 sine theta. So we'll have 3 plus 2 sine theta times sine theta. Okay, so now we've set up our derivative. Now what we want to do is simplify this as far as we can so that when we plug in our value of theta, our angle, it's the easiest calculation that it can be. All right, because in its current state, this derivative is pretty ugly, right? We have 1, 2, 3, 4, 5, 6, 7, 8 different angles, or 8 different thetas that we would need to plug pi divided by 6 into to find the value of the derivative at that angle. And so that would be a lot of extra work that we don't want to have to do. So if we can simplify our derivative further and eliminate some of those extra thetas, that will make finding the slope at that angle a lot easier. So let's work on simplifying our derivative. The first thing that we should do to simplify is distribute cosine through this quantity and sine through this quantity, as well as multiply cosine by itself to get cosine squared theta, which is what we have right here. So if we do all that, dy dx will be equal to 2 times cosine theta times sine theta plus cosine times 3. So we'll have 3 cosine theta plus cosine theta times 2 sine theta. So we'll have 2 cosine theta sine theta. All right, and then that will be divided by 2 cosine theta times cosine theta, which will be 2 times cosine squared theta. And then we are subtracting this sine theta multiplied through this quantity. So we're going to have 3 times sine theta, that's sine theta times 3, and then sine theta times 2 sine theta will give us plus 2 sine squared theta. All right, and then if we distribute this negative through this quantity, we'll have negative 3 times sine theta and negative 2 sine squared theta. So I'm just going to erase these parentheses and change this plus sign to be a negative sign. All right, and now what we can do to simplify this further is combine any like terms and then use some trigonometric identities to make it much simpler. So the first thing that I see that we can do is combine these two terms. We have 2 cosine theta times sine theta and 2 cosine theta times sine theta. Those will combine to be 4 times cosine theta sine theta. So if we do that, this is equal to 4 times cosine theta sine theta. And then don't forget about this other term of 3 cosine theta. So we'll add that to 3 times cosine theta, and then we will divide by this denominator. But what I'm going to do is reorder our terms, and I'll show you why we're going to do that. It's going to make it easier for us to see how to use a trigonometric identity to simplify our derivative further. So what I'm going to do is I'm going to write 2 times cosine squared theta. That's this first term, but then I'm going to write this last term next. We'll have minus 2 times sine squared theta, and then we'll have that last term of negative 3 sine theta. So I'll have minus 3 sine theta. Okay, and so what we can do next is recognize that we have 2 different expressions within this derivative that can be rewritten to be simpler by using some trig identities. Specifically, in the numerator here, where we have 4 times cosine theta times sine theta, we can rewrite that using this identity, that 2 times cosine theta times sine theta is equal to sine of 2 theta. All right, this is a double angle identity. When you have 2 times cosine theta times sine theta, that's equal to sine of 2 theta. Now in this case, we have 4 times cosine theta sine theta. So if we multiply both sides of this identity by 2, that would give you that 4 times cosine theta sine theta is equal to 2 times sine of 2 theta. All right, so we can just replace 4 cosine theta sine theta with 2 times sine of 2 theta. So that will give us that dy dx is equal to 2 times sine of 2 theta plus 3 times cosine theta. And that will be divided by this denominator. And now we can simplify this by using an identity as well. But first, if we pull out this 2 out of both of these terms, we'll have 2 times cosine squared theta minus sine squared theta, and then minus 3 sine theta, right? Both of these terms had a common factor of 2, so I pulled that out, and now we have 2 times cosine squared theta minus sine squared theta. And this expression right here, we can rewrite using a trig identity. We also know that cosine squared theta minus sine squared theta is equal to cosine of 2 theta. This is another double angle identity. We can replace this expression with cosine of 2 theta. So that's what I'm going to do. Let's replace this quantity with cosine of 2 theta, and we'll have that this is equal to 2 times sine of 2 theta plus 3 times cosine theta divided by 2 times cosine of 2 theta minus 3 times sine theta. All right, and now what we have here is the most simplified form of our derivative. Now instead of having 8 thetas that we need to plug our angle into, we have 1, 2, 3, 4 thetas that we have to plug our angle into. It's going to be a lot easier for us to evaluate our derivative and find our slope by plugging our angle into this more simplified form of our derivative. And so let's work on that next. All right, so this was the first part of our example. We have now found our derivative dy dx, right? We wanted to find that derivative, and then we also want to find the slope of the tangent line at this angle of theta equals pi divided by 6. So what we'll do is use this derivative and evaluate it at this angle to find the slope of the tangent line at that angle. So we'll use our derivative dy dx and evaluate it at theta equals pi divided by 6. That will be equal to 2 times sine of 2 times pi divided by 6 plus 3 times cosine of pi divided by 6, and that will be divided by 2 times cosine of 2 times pi divided by 6 minus 3 times sine of pi divided by 6. All right, now 2 times pi divided by 6 is equal to pi divided by 3. So this angle and this angle will be pi divided by 3. So if I rewrite my work up here, this is equal to 2 times sine of pi divided by 3 plus 3 times cosine of pi divided by 6, and that's divided by 2 times cosine of pi divided by 3 minus 3 times sine of pi divided by 6. All right, now sine of pi divided by 3, that's equal to the square root of 3 divided by 2. So this is equal to 2 times the square root of 3 divided by 2 plus 3 times cosine of pi divided by 6, which is also the square root of 3 divided by 2. So we'll have the square root of 3 divided by 2, and this will all be divided by 2 times cosine of pi divided by 3, and cosine of pi divided by 3 is 1/2, so we have 2 times 1/2 minus 3 times sine of pi divided by 6, and sine of pi divided by 6 is also 1/2, so we have 3 times 1/2. All right, now to simplify, this 2 and this 2 will cancel out, right? 2 divided by 2 is 1, so we're just going to have the square root of 3 plus 3 times the square root of 3 divided by 2, and then in the denominator, 2 times 1/2, that's just equal to 1. These 2's will cancel out, and so this is equal to the square root of 3 plus 3 square roots of 3 divided by 2 divided by 1 minus 3 times 1/2, which is 3/2. All right, now we can simplify this further. We know that 1 minus 3/2 will be negative 1/2. So this is equal to the square root of 3 plus 3 square roots of 3 divided by 2 divided by negative 1/2. But dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So instead of dividing by negative 1/2, we can multiply this numerator by negative 2, right? The reciprocal of negative 1/2, we could find that by flipping the numerator and denominator, which will give us negative 2 divided by 1, which is just negative 2. So this will be equal to negative 2 times the square root of 3 plus 3 square roots of 3 divided by 2. Now, if we multiply negative 2 through this quantity, this will be equal to negative 2 times the square root of 3, and then this 2 will cancel out with this 2, right? 2 divided by 2 is 1, so we're just going to have negative 3 square roots of 3. So we'll subtract 3 square roots of 3. And now negative 2 square roots of 3 minus 3 square roots of 3 is going to be negative 5 square roots of 3. So our final answer, I'll write it up here, is that the slope is equal to negative 5 square roots of 3. That is the slope of the tangent line at the angle of pi divided by 6 for this polar equation. Okay, let's look at our next example, which is going to be our last example, where instead of finding the slope of a tangent line at a specific angle, we're going to find the location of horizontal and vertical tangent lines. All right, so here's our last example. We want to find the points of horizontal and vertical tangency, if any, to the polar curve. And we have r equals 3 times cosine theta for the values of theta from 0 to pi. And the reason our angle is restricted in this case is if you were to graph this polar equation, if you're familiar with your polar graphs, you probably know that that represents a circle. Specifically, it's a circle on the right side of the vertical axis in the polar coordinate system. And if you were to find pairs of polar coordinates from this polar equation to graph this, you would find that after the values of theta from 0 to pi, that you will already have made a full circle. So the values after that, from pi to 2 pi, would just make another loop around that circle. So really, we only need to look at the angles from 0 to pi. All right, so that's why it's restricted here, because if you were to look at the values from 0 to 2 pi, you would just find duplicate points of horizontal and vertical tangency. All right, so I just included this restriction to save us some time, so we don't find duplicate points of horizontal and vertical tangency. But typically with these problems, if you don't see this restriction, you're always looking for values of theta for these points between 0 and 2 pi, because a full circle around the polar coordinate system is an angle of 2 pi. All right, this is just a special case where the angles from 0 to pi make up the entire graph or the entire curve. Okay, but anyway, let's work on finding our points of horizontal and vertical tangency. The way that we're going to do that is by first finding the derivative of our polar equation. All right, we're going to use this same formula that we used in the previous two examples. dy dx, or the polar form of our derivative, is equal to this expression. Now what we're going to do once we find that derivative is set the numerator and the denominator equal to 0 separately and solve for the values of theta. Because if this derivative represents the slope of our polar curve, when the numerator is equal to 0, that means we'll have 0 divided by some other value, and 0 divided by anything is 0. So dy dx, or the slope, will be 0 when the numerator is 0. And when the slope is 0, that is where you have points of horizontal tangency. But then points of vertical tangency occur where the slope is undefined. And that will happen when the denominator is equal to 0. All right, when the denominator is 0, you have some value divided by 0, and you can't divide by 0, so the slope is undefined. So that's kind of the process that we're going to use here. We're going to set the numerator equal to 0 to find points of horizontal tangency, and set the denominator equal to 0 to find points of vertical tangency. All right, and if for some reason you find the same value of theta when you set the numerator equal to 0 and setting the denominator equal to 0, it's most likely the case that at that value of theta, you don't have either of those types of tangent lines. All right, you can always check it by graphing your polar equation and seeing if at that angle you do have a tangent line that is vertical or horizontal. But in most cases, if you find an angle where the numerator and denominator are both equal to 0, it's not going to have either of those tangent lines. Okay, but now let's work on this example. We need to first find our derivative, dy dx, and in order to find that, we need to know what f of theta is, as well as f prime of theta. All right, and f of theta is just whatever r is equal to. In this case, r is equal to 3 times cosine theta, so that means that f of theta is equal to 3 times cosine theta. Now for f prime of theta, we just need to take the derivative of this function, and the derivative of cosine is negative sine, so f prime of theta will be equal to negative 3 times sine theta. All right, that 3 carries over, and because the derivative of cosine is negative sine, that's why we have negative 3 times sine theta. All right, so now we can use f prime of theta and f of theta to set up our derivative. So we will have that dy dx is equal to f prime of theta times sine theta. So we'll have negative 3 sine theta times sine theta. So I'll write that down, negative 3 times sine theta times sine theta. Then we'll add that to f of theta, which is 3 cosine theta times cosine theta. So we'll have 3 times cosine theta times cosine theta. All right, and then that will be divided by f prime of theta times cosine theta. So we'll have negative 3 sine theta times cosine theta. So I'll write that down, negative 3 sine theta times cosine theta. And then we will subtract, right? We have a negative sign right here. So we are subtracting f of theta times sine theta, and f of theta is 3 cosine theta. So we'll have 3 times cosine theta times sine theta. All right, so we'll have 3 cosine theta sine theta. All right, so now that we set up our derivative, let's just simplify it a little bit by multiplying sine theta and sine theta to get sine squared theta, and multiplying cosine theta and cosine theta to get cosine squared theta. All right, so this will be equal to negative 3 times sine squared theta plus 3 times cosine squared theta, and this will be divided by this denominator, but notice that we actually have like terms here. We have negative 3 times sine theta cosine theta and negative 3 cosine theta times sine theta. We can switch around the order that these parts are being multiplied in. So we could also have 3 times sine theta cosine theta. And so this is the same term as what we have here. So we can combine them and have negative 6 times sine theta cosine theta. All right, so these are the same terms, so we just added them together. Now one more thing that we can do to simplify. Notice that these two terms have a common factor of 3 that we can pull out. So if we pull 3 out to the front, this will be equal to 3 times negative sine squared theta plus cosine squared theta divided by negative 6 times sine theta cosine theta. And 3 divided by negative 6 will be negative 1/2, right? We can reduce the numerator and denominator by a factor of 3. And if we do that, we will have that our derivative is equal to this numerator. So we'll have negative sine squared theta plus cosine squared theta divided by negative 2 times sine theta cosine theta. Okay, so now we've simplified our derivative pretty far, but we can actually simplify it again. Typically, I don't recommend using your trig identities to simplify your derivative when you want to find horizontal and vertical tangent lines, because oftentimes using the trig identities will make it harder for you to solve for theta. But in this case, we have pretty simple expressions in the numerator and denominator. If we had extra terms being added on in the numerator and denominator, then I wouldn't use trig identities, but in this case it's actually going to make solving for theta a whole lot easier. Alright, so remember the two trig identities that we used in one of our previous examples. We know that cosine squared theta minus sine squared theta is equal to cosine of 2 theta, and we also know that 2 times sine theta times cosine theta is equal to sine of 2 theta. Alright, these are just two double angle identities. We have cosine squared theta minus sine squared theta in the numerator here. If we were to rearrange these terms, we would have cosine squared theta minus sine squared theta, so we can replace that with cosine of 2 theta, and then we have 2 times sine theta cosine theta right here, so we can replace that with sine of 2 theta. So if we do that, this will be equal to cosine of 2 theta divided by negative sine of 2 theta. Remember that that negative is not part of this identity, so it's going to carry over. All right, so we have negative sine of 2 theta. Okay, so now we have our derivative in its simplest form. Now what we can do is set the numerator and denominators equal to 0, solve for theta, and find our points of horizontal and vertical tangency. All right, and so let's start by finding our points of horizontal tangency. Remember that points of horizontal tangency occur where the slope is 0, and that's going to occur when the numerator of our derivative is equal to 0. All right, so we'll have 0 is equal to cosine of 2 theta, and so when is cosine of 2 theta going to be equal to 0? Well, we know that cosine is equal to 0 when theta equals pi divided by 2 or pi equals 3 pi divided by 2, but in this case we have 2 theta, and so what we can do is set 2 theta equal to pi divided by 2 and 2 theta equal to 3 pi divided by 2. Those are the two angles that make cosine equal to 0, so all we have to do is figure out what value of theta will make this angle pi divided by 2 or 3 pi divided by 2. All right, so if we divide both sides of these equations by 2, we'll have theta is equal to pi divided by 4, and theta is equal to 3 pi divided by 4. So if we plug these two angles into this equation, you'll have pi divided by 4 times 2, which will be pi divided by 2, and cosine of pi divided by 2 is 0. And then for this angle, we'll plug that in. 2 times 3 pi divided by 4 will be 3 pi divided by 2, and cosine of 3 pi divided by 2 is 0. Okay, so those are our two angles where we will have horizontal tangent lines, and we'll plug those values of theta into our polar equation at the end to find our full coordinate points, because we do want to find the points of horizontal and vertical tangency. But before we do that, I want to find our angles for vertical tangency. All right, and vertical tangent lines occur where the denominator of our derivative is equal to 0, where the slope is undefined. And so if we set that equal to 0, we'll have 0 is equal to negative sine of 2 theta. Now if we divide both sides by negative 1, we'll still have 0 on that side, and that will be equal to sine of 2 theta. And now we just have to determine, when is sine equal to 0? Well, we know that sine is equal to 0 at 0 and pi, right? Sine of 0 is 0, and sine of pi is 0. So we'll set those angles equal to 2 theta, so we'll have 2 theta equal to 0, and 2 theta equal to pi. If we solve for theta, that will tell us what value of theta will make sine of 2 times that angle equal to 0. So for this first equation, dividing both sides by 2 to solve for theta will just give us theta is equal to 0, because 0 divided by 2 is 0. So theta equals 0 is one of our angles where we'll have a vertical tangent line. And then if we solve for theta in this equation by dividing both sides by 2, we'll have theta is equal to pi divided by 2. And so you can see, when theta is 0, or pi divided by 2, sine of 2 times theta will be 0. When theta is 0, you have 0 times 2, which is 0, so we'll have sine of 0, and that's equal to 0. And then when theta is pi divided by 2, you'll have pi divided by 2 times 2, which is pi, and sine of pi is 0. All right, so 0 and pi divided by 2 are angles where we will have vertical tangent lines for this polar equation. All right, and just remember to check to make sure that none of your angles for your vertical tangent lines are the same as your horizontal tangent lines, because if they are the same, then you're going to eliminate them. You're probably not going to have either of those types of tangent lines at those angles. All right, and we don't have any overlap here, right? We have pi divided by 4, 3 pi divided by 4 for horizontal, and 0 and pi divided by 2 for vertical. So we're good. Now what we have to do is plug in these values of theta into our polar equation to get the full polar coordinates, or the full points. So let's start by finding our points of horizontal tangency. For horizontal, our first angle is pi divided by 4, so if we plug that into our polar equation, we'll have 3 times cosine of pi divided by 4, and cosine of pi divided by 4 is the square root of 2 divided by 2, so we'll have 3 times the square root of 2 divided by 2. So our first point will be 3 times the square root of 2 divided by 2, comma pi divided by 4. Then our second point, our angle is 3 pi divided by 4, and cosine of 3 pi divided by 4 is the negative square root of 2 divided by 2. So we'll have 3 times the negative square root of 2 divided by 2 as our value of r. So we'll have negative 3 times the square root of 2 divided by 2, and then our angle of 3 pi divided by 4. All right, so those are our 2 points of horizontal tangency for this polar equation. Now let's find our points of vertical tangency. Our first point is where theta is equal to 0. And when theta equals 0, we'll have 3 times cosine of 0. And cosine of 0 is 1, so we have 3 times 1, which is 3. So our value of r will be 3, and our angle is 0. And then our second point is when our angle is pi divided by 2. And plugging that in, cosine of pi divided by 2 is 0, so we have 0 times 3, so r is equal to 0. So we'll have 0, comma, pi divided by 2. Those are the 2 points of vertical tangency for this polar equation. Okay, and so now we're done. We found these 4 points, which make up all the points of horizontal and vertical tangency for the polar curve represented by this polar equation. We have 2 points of horizontal tangency and 2 points of vertical tangency. All right, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.